The A-37 is powered by two J-85-17 engines, each developing 2,850 pounds of thrust. We will first discuss the engine and its basic components, then the information you must know concerning normal operating limitations. Because both engines are identical, what is said about one will apply to both. The basic engine is composed of 6 main sections: the front frame, compressor, main frame, combustion section, turbine, and exhaust. We will briefly discuss each section to acquaint you with its function and to give you an appreciation of the need to operate the engine within its operational envelope. The front frame section contains the variable inlet guide vanes. These guide vanes direct the flow of air to the compressor section. They are movable and are operated by the fuel control. They function at all airspeeds and altitudes to prevent compressor stalls by providing the correct airflow to the compressor. Each of the guide vanes is hollow, as well as is the nose cone, permitting hot bleed air, when selected, to circulate throughout to prevent ice formation. Anti-ice must be selected by the pilot, however. The compressor section takes the air through a series of stator and compressor blades and compresses it. The compressor is turned by a shaft connected to the turbine in the back of the engine. As the air is compressed, its temperature rises. Two sets of bleed air valves permit a portion of this compressed air to be released as necessary to maintain correct engine pressure. Hot bleed air is also used for the aircraft air conditioning and defrost system, yaw damper, and anti-ice. This slide shows the bleed valve duct for the anti-ice system. The main frame contains the fuel manifold, which sprays measured fuel into the hot compressed air just prior to entering the combustion section. Also located on the main frame is the accessory gearbox, which we will discuss in a few minutes. As hot compressed air and fuel enter the combustion section, some of the air is circulated around the burner can for cooling, and the rest enters the burner can or combustion chamber, where it is ignited by igniters during starting or by the sustained flame after starting. This engine does not have continuous ignition to prevent flameouts. The expanding hot gases escape rearward and turn two turbine wheels mounted on a common shaft with the compressor section. After turning the turbine, the gases are again slightly compressed and directed by the exhaust section for thrust rearward. The thermocouples projecting into the exhaust flow measure the exhaust gas temperature to monitor engine performance. This has been a brief explanation of engine components and their operation. Study these EGT limitations. The mainframe contains the accessory gearbox, which is a conglomerate of pumps, valves, and tubing. The accessory gearbox wraps around the lower center section of the engine and contains the hydraulic pump, fuel pump, starter generator, fuel control, oil pump, and overspeed governor. The starter generator turns the entire gearbox, all the pumps, and the engine during starting. Damage in one of the pumps or in the engine could cause the generator shaft to break at a shear point on the shaft. This shear point prevents further damage to the generator or other components. In previous lessons, normal engine operation has been discussed. Now let's review some engine operating limitations you should commit to memory. Estimated engine life is based on metal fatigue. Over temperatures cause uneven and excessive deterioration of engine parts, as well as severe wear to the engine in general. Usually, out-of-limit temperatures indicate a malfunction of the fuel control or operation of the engine out of its operational envelope. If operational limitations are exceeded and the engine shuts down, do not attempt a restart until investigated by maintenance. B is the correct answer. If light-off has not occurred after 15 seconds, the engine is either not getting fuel or ignition. You should abort the start immediately. B is the correct answer. Although within limits, a starting EGT above 900 degrees for 2 seconds would not be normal. As with any aircraft, Engine fluctuating oil pressure, or loss of oil pressure, warns of impending seizure. The A-37 engine oil system is not designed for negative G flight of extended duration. Do not exceed 30 transits from positive to negative G condition per flight, or 60 seconds total negative G per flight. We frequently operate single engine to save fuel. When operating single engine, alternate engines every 30 minutes to provide lubrication and to prevent excessive oil loss from windmilling RPM. The tachometer is mounted on the engine oil pump. Sudden loss of an RPM indication could indicate possible oil pump failure. You should monitor oil pressure on that engine carefully and use other engine instruments to set power. Answer C is correct. The A-37 oil system will not provide lubrication for extended periods of negative G. B is the correct answer. A windmilling engine will not provide enough oil pressure to adequately lubricate the engine. Answer A is correct. The tachometer is mounted on the oil pump and will fail with the oil pump. The engine speed is regulated by an overspeed governor for high speeds. In the event this governor malfunctions, the pilot has the responsibility for maintaining engine speed within limits. Flight conditions during climbs and dives may result in temporary RPM increases. When these conditions occur, throttles should be adjusted to maintain engine speeds below 100%. Operation in excess of 103% constitutes an overspeed and should be logged in the 781, noting highest RPM, EGT, and duration over 103%. If you will study this diagram, you will see that fuel is used for three purposes once in the engine: for combustion, for positioning the variable inlet guide vanes, and to cool the oil. Review this diagram for a few moments. On the ground, idle should be 46.5 to 49.5%. In flight, the pilot must maintain the idle, as this engine has no automatic idle control. As you can see, a rollback or flameout is possible if you do not maintain minimum idle RPM. Study this chart to see the minimum RPM settings for different altitudes. A is the correct answer. There is no in-flight idle control on the engine. This seldom presents a problem during normal operations. However, at high altitude, pulling the throttles to idle could cause a rollback. Engine rollback and compressor stalls are an in-flight hazard to all operations. Carefully study these paragraphs extracted directly from the -1. The left engine is provided with an ice warning probe, which detects pressure changes as ice accumulation occurs on the probe. When this occurs, the engine ice light on the annunciator panel will illuminate to warn the pilot. You should immediately turn on the anti-ice, if not already selected, and climb or descend out of icing conditions. The ice detect probe contains a heating element, which will automatically turn on and melt the ice off the probe. If still in icing conditions, the engine ice light will come back on and the cycle will repeat. With DC failure, there will be no ice warning. Remember, the heater only de-ices the probe, not the engine. The aircraft has no de-ice equipment, only anti-icing to prevent ice accumulation. Once you have ice accumulation, you must get out of icing conditions to remove the ice. Rapid throttle movement will cause pressure changes in the intake, which may momentarily cause the engine ice light to illuminate. The anti-ice switch controls two shutoff valves in the bleed air line, one to the engine and one to the nacelle anti-ice areas. Placing the switch on will allow the valve to open. With DC failure, the valve will fail-safe open and anti-ice will remain on. An increase in EGT of approximately 10 to 20 degrees will indicate operation of the system, and the inlet heat caution light on the annunciator panel will illuminate. With the anti-ice switch in the off position, no anti-ice protection is provided. This system is independent of the air conditioning system and bleed air switches. The anti-ice switch is on the air conditioning panel for convenience only. The anti-ice system should not be activated at ambient temperatures above 40 degrees Fahrenheit, except for checkout. Extended usage above 40 degrees Fahrenheit could cause an overheat in the forward nacelle area. C is the correct answer. Most engine problems develop when pilots attempt to operate it out of the envelope or exceed operating limitations. B is the correct answer. The anti-ice system will fail-safe to the on position. B is the correct answer. Extinguishing of the light only indicates that the ice has melted off the probe and not that you are out of icing conditions.